about number 20, with the wrecking ball. Okay?
You want me to record this?
Yes. Oh, we're recording? We're good? Okay. So here's your basic setup. So you might have to spin that over just a little bit greater. So imagine here's the wrecking ball, right? So you're going to lift this thing up to a height of, I think it's like 25 degrees, something like that.
Yeah.
Okay? So here's your setup. When you lift this up, you're going to do a certain amount of work, okay? And you're going to store this thing as potential energy. So what you have to find is that net height difference between where is that at its equilibrium point and where it is at its highest point, okay? Now, because energy is a scalar quantity, the path that it takes doesn't make any difference. It's like, okay, hey, over Thanksgiving, let's say Cassidy is going to Chicago, okay? Right? So she can fly from here to St. Louis up to Chicago. She can fly here to Denver, Denver to Chicago. She can just drive straight to Chicago, okay? The net effect is Cassidy's going to end up in Chicago, okay? The path that she takes doesn't matter. She's going to end up in Chicago. So when I look at this coming up like this, we need to figure out what this height is from that equilibrium point to here. Because it doesn't make any difference if I just lift this thing straight up, okay, and store that amount of energy, or if I lift it up on an arc like this. The energy change is going to be the same. So what you want to do is use this equation that's at the bottom of that page, which is L minus L cosine theta. If you want to factor out an L, you could write it as L times the quantity 1 minus cosine theta. It's the same thing. So this is just plugging numbers in. You've got that length of 15 meters. You got the cosine of 25 degrees. What that gets you is the net effect of lifting this thing up. Okay? So then once you get that, then it's just a matter of plugging it into MGH, equals MGH. So that one on number 20 should be something times 10 to the 4th joules. Now, let's talk about 32. 32 is a good question. So, if you look at what's happening on number 32.
Oh, yeah, this one.
So, this one you've got a hill, right? And the hill is like 5 meters, and then you're going to end up 5 meters down here. Okay? Now, there's a couple of ways you can approach this problem. I don't care how you handle this, okay? But this is what you have to understand. So, 1,500 kilogram car approaching a hill, right, 10 meters per second, runs out of gas. Can the car make it to the top of the hill by coasting? So here's the deal. So one option is that you set up a chart. You go, okay, I'm going to have UG, I can have kinetic energy, I can have the sun, right? So when this car is just moving on level ground, what's the only type of energy that it has?
Kinetic.
Kinetic. Oh, okay, right. So this is your coast column. You have to, at that point, you don't have to worry about any gravitational potential energy because it's just all kinetic. So you have the mass, you have the velocity, you can calculate how much kinetic energy that it has, right? So you do that, you can figure this out. So then you can figure out, okay, once you get this number and you know that sum, okay, that's how much energy that we have. Then you can say, okay, well, how much energy would it take to move up that height, okay? Then you can go, okay, well, if I go to the top, if I'm up there at the top, okay, how much energy is that going to take to lift that up? Oh, okay. And if that amount of energy that it takes to move up to that height is less than the kinetic energy that you have, it's going to make it up the hill.
Equal to, right?
Yeah.
As well.
Yeah. Now, that's one option. Okay, that's an option. Okay, just look at the numbers. Oh, is it going to make it up? Now, the other option is you can say, okay, well, if I take all of that kinetic energy and translate it all into potential energy. So in other words, if I take all the kinetic energy that I have at the bottom and I take all of that kinetic energy, and I empty my kinetic energy container, and I put it all in my UG container. Okay, so if you like the container analogy thought process, you go, okay, well that's going to be 1/2 mv squared equals mgh. So if I take all the kinetic energy and say, okay, I'm gonna go all in. I'm gonna cash in all my chips, and I'm gonna put this all into my UG container. Your masses are gonna cancel out. And you can solve this for h. So you would have 1/2 v squared divided by g, and find the maximum height that you could swing this up to. If that value is bigger than 5 meters, it's going to make it up the hill. Okay? So you can either look at it from an energy perspective, or you can find the maximum height that it could go up. If that maximum height is 5 meters or greater, it's going to make it up the hill. If it's 4.9 meters, it's not going to make it up the hill. If you have a certain amount of joules of kinetic energy and it takes more joules of that energy to make it up the hill, you're not going to make it up the hill. So you can take either approach, okay? I don't care. It's up to you. I don't care how you do it, but just make sure that I see what you've done, okay? Now, then you get to B. If your answer to part B is yes, which it should be, okay? You should see that it makes it up the hill, okay? Then it says, what's the card speed after coasting down the other side? Okay, now, here's the deal. When it goes down the other side, right? Okay, so here's the easiest way to approach that. Is say, okay, here you have all kinetic energy, right? It's all kinetic. Just leave the hill out and say, okay, when I get back to this point, it's all going to be kinetic energy again. And then figure out how much UG energy you're going to get from going from here down to here using mgh. Add those two values together, boom, there's your final velocity. Now let me show you a cool trick, because this also plays out on question number 5 on the sheet that I've got. So let's look at a little bit of voodoo. Okay, so this is number 5, and it's also this second part of number 32. So when you have something up on top of this hill, or just up above the ground in general, you have two things that can happen. You know you're going to have UG, okay, without fail, you know you're going to have UG, right? Now, you could potentially have some initial kinetic energy. So if I take this ball and I throw it up in the air, or if I throw it down, if you think about this, I'm going to have two types of energy. I'm going to have UG because it's above the ground, and then I'm going to have kinetic energy because I'm going to throw it, okay? So these two values up here at the top have to equal all of the kinetic energy at the bottom, okay? Because when you hit the bottom, it's all going to be kinetic energy because you're not going to have any UG. Okay, so we can write this as mgh, and that's 1/2 mv naught squared, and that's 1/2 mv squared. Okay? Now here's the cool thing. Michael, what's going to happen to that mass?
It's going to cancel out.
It's going to cancel out. All the masses go away. Okay? Now, since I hate fractions, what am I going to do at this point?
Multiply by 2.
Multiply by 2. So I'm going to get 2gh plus v naught squared equals v squared, which oddly enough is just nothing more than that equation. Okay? So that equation comes out of the idea that energy is conserved. Okay? That's all it is. So that equation just comes from energy. Now, here's the beauty of this. This is what I want you to think through. Go back up to this idea. Now, let's focus. This is the misconception or the conception that you have to get straight. Let's look at this velocity right here, this kinetic energy. So let's say I throw this thing at 10 meters per second, and I throw it up, and then I'm going to throw this thing up, and then I'm going to have it all the way go down to the ground. Situation number 2, I'm going to throw it with the same velocity, but I'm going to throw it horizontally, and then I'm going to have it hit the ground. And then I'm going to throw it down, or I'm going to throw it at an angle, or whatever I want to do. As long as I throw that thing at 10 meters per second, does it make any difference which direction I throw it in terms of my final answer? No, doesn't make any difference. Because kinetic energy is a scalar quantity. The direction I throw it doesn't matter. So if I throw it down, if I throw it at an angle, if I throw it straight up, it doesn't make any difference. I can throw it down like this. As long as I throw this thing with the same initial velocity, from the same height, it's going to land with the same final velocity. Now, here's what's going to be different. Especially when you throw it at like an angle of 45 degrees or something like that. When it lands, this is where it turns into like basically a Pythagorean theorem. When it lands, it's going to have some horizontal velocity and it's going to have some vertical velocity. Oh, then you get into v squared, vx squared plus vy squared is going to equal v squared. So it's a Pythagorean theorem because you're going to try and find that resultant velocity. So even if I throw it at an angle, if I throw it horizontal, it doesn't make any difference. When this thing lands here, it's still going to have the exact, and this is the terminology you have to get right. This is going to be the same speed here as if I just throw it and it falls straight down. So if I throw it up, it's going to land with a certain speed. If I throw it horizontally, it's going to land with a certain speed. Because up at the top, it has UG and it has kinetic energy. But when it lands, no matter what's going on, it's still going to land with the same final kinetic energy. The angle that I throw that thing does not matter. Okay, it does not matter because all of that kinetic and all of that potential is going to be all kinetic at the bottom, so the angle doesn't matter. So I can throw it like that, I can throw it like that, I can throw it like that. Doesn't make any difference. As long as I throw it with the same velocity, it's going to land at the same speed and the same amount of total energy. Okay? Because it's a scalar quantity. It doesn't make any difference which direction that you throw it. Okay? So, that's what I was trying to get you to see on number 5. And on 5, on the questions that I gave you, that last, because it all kind of builds off of each other. So, that answer on 5D should be on a weighted GPA, pretty good. Okay? That's got to be a weighted GPA, not a straight 4.0. So, there's that.
So,
Yes?
32B, like, would you, so if the kinetic energy go, like, to reach the top is greater than what's at the top, did you have kinetic energy left over?
Yeah. So
Going
it just
down.
means it was still moving.
So you just add that to the car's potential energy at the top of that new height as it goes down, right?
To get
The
what?
total kinetic
Yes.
energy at the bottom?
That's one option that you can do, yes.
Alright, so that's about our age minus 4?
I'll give you that,
Alright.
yeah. Assuming that you're not 30, yeah.
Okay.
So, you know,
30-year-old in disguise.
assuming that you're like a standard age of a senior in high school, you know,
Alright.
you're not like Dookie, you know, some, you know. Anyway, yeah. Your, on number 28, your answers to A and C on 28 should be in the 20s. Okay? Just kind of a ballpark. Your answer to 30 would be a pretty good GPA as well on a weighted scale. On number 4, on the questions that I gave you, because that builds off of each other, that answer to 4C should be around 90 meters.
Feel right.
And all of your answers to number 6, on the ones that I gave you, all should start with a 1. And some of them should be times 10 to the 3rd. Others should be close to your age. Okay,
What'd you get for the multiple choice?
got it? Good. Any questions? Going once? Going twice?
Oh, 27.
Oh, seriously?
Sorry, I'm that guy.
What?
Number 27 on the book.
Yeah.
Questions. Just like, could you parse that out for me?
Oh, the question?
Yeah. Like,
Seriously.
I know.
Okay. So, let me try to lay that out. This one's on like an incline.
Yeah, it was velocity over 2. Oh, 6. 17, 50, and 18, 17. And about 17 meters. See? I think I did this like backwards. I found like this before I was supposed to. You might check with Christian. Yeah, I did that before. I did like the height shoot up thing with that equation.
Okay. So if you don't want to do smash mouth physics, okay, kind of the more elegant approach. So here's the whole kicker. When this thing starts, what's the only type of energy that it has?
Potential.
Right? So that's how much you bring to the bank, okay? 100 joules, whatever that is, right?
Yeah.
Now, so it's going to slide down, and then it's going to start going up this hill, right? So as it goes up the hill, at any point, that's going to equal the sum of that new potential energy plus some amount of kinetic energy, right?
Okay.
Now, you're specifically told you want this to be half of, what is it they want it to be? What's V over 2?
V over 2 equals
Yeah,
what?
because when it got down here, it would be at some V.
Yeah.
So you want this just to be V over 2.
So you find height when it's
Yeah, so then if you're clever, you can cancel out all the masses. That's why you're not giving the mass to the block.
yeah. I knew that.
Okay?
And then,
Now, if you like smash mouth physics, make the height 1 meter, make the mass 1 kilogram, work out the ratio that way.
all right.
So personally, I'd cancel out all the ends. I'd multiply everything by 2, get rid of the fractions, and then go from there. So that's how you start.
Oh, okay. Yeah.
Anything else? Going once, going twice? So 2 3/4, 2 7/8,
Squared
2 15/16. So yeah, I kind of like it.
I'm doing okay. 6 on this record. At what height the car go?
So that's like
I did it in a very unelegant way.
Stop that camera for a second. So this is kind of going to go old school back to the very first lab that you all did in this class. Okay, the very first lab that you all did. Of course, I had COVID at the time. But you took a spring and you hung a weight from it and you measured how far it stretched, right? It's like, ooh, we're doing science, right? And at the time I said, you're going to take this mass in kilograms, multiply it by 9.8 meters per second squared, and you all were going, okay, cool, we'll do this in we'll go from there, okay? And when you all did that, and at the time, you plotted force on this axis in newtons, and you plotted elongation on this axis, right? Now, on this graph, why did you plot force here and elongation there? Evan?
Because you were, the force was like the,
Keep going.
variable you were changing.
Independent variable.
Independent variable.
There you go.
Whereas the elongation was the dependent variable because you were measuring it.
Fantastic. And and this elongation was dependent upon the amount of force, right? And you all did this graph, and you were cool, and you drew this line of best fit, and you said, oh, we're doing science, okay? Okay, and life was good. And now I'll guarantee if I could go back and give you that same line, and you're like, oh yeah, okay, whatever. So we got this. Yeah, we got it. Now, but here's what's going to be important, and this is in terms of understanding springs, is that this is a linear relationship, right? Okay? So the more force that you apply, the more elongation that you get. Okay? So that's the basic idea. Now, when you're talking about springs in terms of energy, and you all did this graph as well, you guys, I had you switch it up. I also had you draw another one where you put force on the y-axis and elongation on the x-axis. And that was also a linear relationship. Okay? So that's kind of cool, right? Now, if you're talking about springs in terms of energy, and you'll see why this has to work out. When you're dealing with energy of springs, you have to have the graph like this. You have to have force on the y-axis and elongation on the x-axis. So here's what we're going to look at. Let's just say, let's make up some numbers. Let's say that that took 20 newtons of force, and that created an elongation of 0.20 meters, okay? About 0.20 meters would be about like yay, right? 20 newtons of force, that'd be like 1 kilogram masses that were hanging from the spring, right? And this is going to start at 0, 0, because we know with no force we don't have any elongation, right? So if I know that that's 20 newtons and that's 0.2, and I'm starting at 0, 0, can I find the slope of the line?
Yes.
Sam, what would the slope of that line be? 20 newtons minus 0 divided by 0.20 meters minus 0. So what do you get? What's 20 divided by 0.2?
100.
100. Now, what units do I get? Do I get Newton meters, or do I get Newton per meter? There's a huge difference.
Newtons per meter.
I get newtons per meter, okay? This is not Newton meters, okay? If I cannot emphasize this enough, this is what everybody screws up. Oh, you get Newton meters. No, I get newtons per meter. Eli,
So if you were to find the area, would it be Newton meters?
we'll get that. You're to step 3, I'm on step 2, but you hold that thought, okay? That's going to be an important part. So, the slope of this line is what we call the spring constant. So, this is going to be the spring constant. And the spring constant is shown by the letter K. Okay? So here's what we've got. This is very much a linear relationship, right? We can put this as y equals mx plus b. So in this case, we're going to have y equals mx plus b. I don't have to worry about the y-intercept part, okay, because that's gone, because I don't have any. So force is on my y-axis. Slope is that spring constant. And my elongation is going to be here. So if you have springs, okay, so this is the force. There's your spring constant. And there's your elongation. Okay? So here's what's gonna be important that you get out of this, and this is what's different from forces that you all are used to working with. You all are used to saying, hey, you know, here's the calculator, and I wanna push that calculator a certain distance. Here's the paradigm shift that you have to make. You all are used to that force staying constant. Oh, I'm gonna push that force over a certain distance. And when you did that, when you drew your force and distance graph, that was a horizontal line, because you were applying the same force over the same distance, okay? And up to this point, that's what's always happened. You applied the same force over the same distance, okay? And it's been a horizontal line on a force distance graph. With springs, you can't do that. With springs, it's a sloping line. So with springs, if you're talking about like how far you stretch it, or if you're talking about like with the marble launcher, when you talk about how far you compress it, okay? The more you compress it, the more force it takes. The more you stretch it, the more force it takes, okay? So with your dealing with springs, you have to get out of this mindset that, oh, I'm gonna apply the same amount of force over this distance. This is a linear function, okay? The more you stretch it, the more you compress it, the more force that it takes, okay? So when you're dealing with springs, your force distance graphs are not horizontal lines. Your force distance graphs are gonna be sloping lines, okay? Now, with that said, let's talk about what Eli said, okay? So if we've got this graph, so let me kind of redraw this graph so we can restart. So we had force here in newtons, and we had elongation here in meters, and we had that sloping line, right? And we said that F equals kx, right? Cool with this. Now, Eli, if I asked you to find that area underneath, and it stretched a certain distance and that required a certain amount of force, how would you find that area? Mathematically, what would you do?
1/2 times base times.
So this area would be 1/2 base times height. True? Now my base is going to be my x, and the height is going to be my force, right? So I have 1/2 x times force. Now, we just said though, because it's a linear relationship, that F equals kx. Oh, that's kind of cool. Let's do a little substitution. Let's put that in here. So now area is going to equal 1/2 x times kx, which is going to give me what? 1/2 k x squared. Oh, that's kind of punchy. Okay? Now, with that area, that's going to equal us, because that's going to equal the energy that I store in that spring, because that's going to equal the work that's done. So, on a elongation force graph, the area represents the work. It also equals your elongation. Okay? Oh, excuse me, the change in us, it equals the work, because you're plotting elongation versus force. So here's what's going to be important, okay? You have two equations that relate to springs. You have us equals 1/2 kx squared. You have F equals kx. Now, here's what I want you to see. Assuming that you have the same spring constant. If your spring constant is the same and you double the elongation, what happens to the amount of force? It's going to double, because this is a straight linear relationship, right? Okay? So if I'm at, remember, this isn't the length of the spring. This is how far it stretches, okay? Listen to me. It's how far it stretches. So if I'm here, it's going to stretch a certain distance, okay? Certain elongation. If I double that elongation, that's going to take twice as much force. So if that was the elongation with 0.2 kilograms, which is about 2 newtons, okay? If I put 0.4 kilograms on there, that should stretch twice as far. So force and elongation is a straight linear relationship. But if I double the distance, what's that do to the amount of energy that I store? Then it quadruples, because that's x squared. So if you double the distance, you quadruple the energy that you store. But if you double the distance, that just takes twice as much force, okay? So this one, double, double, that one, double, quadruple, okay? Triple, 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 increased by 9, okay? So you have to keep in mind these two equations. They both involve x, right? One of them is x squared, the other one is x. So you have to pay attention. Is the question asking about force, or is the question asking about elongation, okay, and energy? You have to keep that straight. Okay. Now, for those of you that are calculus nerds, so if you look at this being a linear relationship, okay, where you have the slope of that line is going to be like some constant k, right? Okay, which is just going to be the slope of that line. And if you want to find that area underneath that line, so what do you do when you try and find the area underneath the line? What do you take? The derivative or the, well, I used to call them integrals. The derivative or the antiderivative?
I say integral.
Huh?
I say integral.
What?
Integral.
That's right, because you want to find the area underneath that line. So if you look at this and go, okay, well that's kx, okay, which is going to define that function. Then if you do an integral, you raise that, whoa, come back here, like to the second power, and then you put a 1/2 out in front of it. You end up with the exact same thing
Oh my gosh.
of 1/2 kx squared, okay, because it's a sloping line. So there's your application to calculus, okay? All right, you've been sitting for a little bit, stand up, take a quick stretch, and go from there.
So is the spring constant, is that a force over meters? Alright.
And then you can find where you're supposed to use the
Homework at home.
antiderivatives, you take the
I
next.
was busy watching the Lakers.
Next power.
Dylan said
After school, and then I go home. And
No, in the distance from it to a different length.
Actually defining a category
There's a reason. I know, and it got from 80
Redefining a group of people as
And then
I get it. I do it out of I can do it out of the box.
to the area of just make
I will agree. I got dressed up. I was about to say.
I spent so much time doing contracting.
Well, I didn't
I would like
who would have thought that a black hole would weigh that much?
Were you trying to bring all black up?
I feel like a black hole is like the absence of something.
I couldn't
I
find
guess I was wrong.
a shirt that goes with this hoodie.
Why did your shirt so
Dude, why does a black hole have to wait? Does that mean like if a black hole lands on you?
Yes. You would very much die.
Are we ever gonna learn how black holes work? Just work
No, not really.
I said not really.
we still will. How much force does a black hole create if it's 1 million miles from If there was a...
I do think that tells me
The universe
They say that there was one like near Mars or something like that. Dude, what if we never died though?
Okay,
I left that camera rolling.
we'll stop it now. That way I can splice that in.
Like Batman.
Okay. So far, all the energies that we've dealt with have just been kinetic and gravitational potential. Now we're gonna throw springs into it.
Yay.
Okay? So, picture this. So this also harkens back to one of the labs that we did back when we were studying like velocity time graphs. Remember, you pushed the card into the wall and it hit and it bounced back, and you had to draw like the velocity time graphs. And you're going, oh my God, Mr. Burkamp, this is so hard, okay? And, you know, if you remember, the velocity time graph looks something like this, okay? And that's like when the spring hit and stored potential energy and the spring expanded, right? Oh, wow, this is just hard, okay? Now you're going, really? You struggled with that? Yes, you did. So don't get cocky. All right. So now we're going to look at the exact same situation, but now we're going to look at it from an energy perspective. So imagine, if you will, you have a cart with a mass of 0.3 kilograms, kind of like this, and it's got a plunger out in front of it, which has a spring constant of 3.00 times 10 to the third newtons per meter. Now, to give you some perspective, like this spring here that you've worked with before, that has a spring constant of about 80, okay? So the higher the spring constant, the stiffer the spring, because that means it takes more and more force to compress it or stretch it a meter, okay?
Is it either way?
So this is actually a pretty stiff spring.
It is.
So visualize this. This cart is rolling along, it's gonna hit the wall, and then it's gonna bounce back. So, harken back to the day Wall got his nickname, okay? So, when it's moving along like this, what's the only type of energy that it has? Kinetic, right? We're just rolling along, there's no hills involved, it's just kinetic energy. Now, as it hits that wall, what's going to happen to that kinetic energy?
It goes down.
It's going to decrease. Now, when that spring is fully compressed, how much kinetic energy is it going to have?
Zero.
Zero. Because it's all going to be us, right? Now, it's the same idea as if I threw this thing up in the air. If I throw it up in the air, what happens, as soon as it leaves my hand, what happens to the kinetic energy? It decreases. What happens to my UG? It increases. Can I have both us and UG?
Halfway, yeah.
Or even at any point, up until it reaches its maximum height, right? Okay? And then, once it falls, my UG is going to decrease, and my kinetic energy is going to increase. So the same thing's going to happen here. When that spring hits that wall, what's going to happen to the amount of kinetic energy in the cart? Spring hits the wall. The amount of kinetic energy is going to begin to decrease. What's going to happen to the potential energy stored in the spring?
Go up.
It's going to go up. So if you were to draw a graph of energy, so we'll put energy in the spring here, we'll put kinetic energy of the cart up here. So right as it hits the wall, it's all kinetic energy, right? You have no us. But as that spring gets compressed, what's going to happen to us?
It's gonna increase.
Us is going to increase. What's going to happen to the kinetic
It's
energy?
going to decrease.
It's going to decrease. Now, at what point is there going to be no kinetic energy?
When it's fully compressed.
When it's fully compressed, that's when that's all going to be us, right? Now, does Mother Nature like us?
No.
Mother Nature likes kinetic energy. Because if Mother Nature liked us, what would happen?
It would stay.
It would stay right there. Mother Nature doesn't like us. Mother Nature goes, screw you. I'm going to go back to kinetic energy. Because if she preferred us, it would stay there, which would get really weird. Okay, because springs wouldn't do us any good. Oh, hit the spring, whoop, and then it just stops. It's like, well, that was cool. Okay, mouse traps. Guess what? Wouldn't work. Well, because Mother Nature would like the energy stored there. Maybe it has something to do with mice. I don't know. Now, so as soon as the spring begins to expand, what's going to happen to us? It's going to decrease. What's going to happen to kinetic?
Increase.
It's going to increase. Whoa, you guys going, whoa. Okay, this is weird. All right. So, here's what we're going to look at. So, I've got a cart. It's moving at 2.5 meters per second. Has a mass of 0.3 kilograms. It's going to hit the wall. The spring constant is 3 times 10 to the third. When that spring has been compressed 0.1 meters, 1 centimeter, okay, so imagine this spring is going to compress 1 centimeter. I want to know how much kinetic energy it has and how fast it's going. So where are we going to start? Let me give you a hint. It rhymes with art.
Fart.
That's what I was thinking. Start.
Chart?
Chart.
Chart. That's why I don't teach freshmen.
I did this.
So now we need to add on to our chart. Now we can have KT, we can have us, and now we can have us. Still going to be the sum, right? Now, when it's rolling, how much UG does it have?
0.
0. We got nothing. Has the spring has the spring compressed at all?
No.
That's 0. What's the only thing I have?
Kinetic.
Kinetic energy. Do I have enough information to calculate the kinetic energy of the cart?
Yes.
Yes. I had mass,
And velocity.
I've got the velocity, right? So I can calculate the kinetic energy of yonder cart. Yonder. So that's going to be 1/2 mv squared. Mass was what, 0.3 kilograms? And the velocity was 2.5, yep. So somebody take 2.5 squared times 0.3 times 1/2.
0.938.
0.938 joules. Now, here's the cool thing about this, okay? That means at any point, what do all my energies have to add up to?
0.938.
938. That's it, okay? So if this number is wrong, everything is going to be wrong, okay? Everything you do from there on out is going to be wrong. But here's the beauty of this chart, is that it's like, okay, now I know what I've got. Now, if you reverse this and said, okay, I'm going to start with that spring being fully compressed. So in other words, I'm going to start this and saying, okay, bless you. I'm going to have it like this. Now, if it's like this, what's the only type of energy that you would have?
Spring.
Spring, and you would have no KT and you would have no Now, imagine that you could put it up on a ramp. Then it would only have, but then it would roll down and it would gain,
KT.
and then it would roll along and have kinetic, and then it would change that into, look for a problem like that coming near you, where you have all 3 types of energy, okay? You can handle it. I got faith in you. I got faith. All right, so if you go to what I want to find out next, I'm going to compress this spring 1 centimeter. I want to figure out how much kinetic energy I have left over and what's going to be the velocity, right? Now, I don't have to worry about UG because I'm not going up a hill. Okay, so I don't have to worry about that. Do I have enough information, since it's compressed 0.1 and I know the spring constant,
Yes.
can I calculate us? Right?
1/2.
So us is going to be 1/2 that K of
0.001.
times 10 to the third newtons per meter. And that was 0.010 meters squared. Now, this is why, when you do your graph, this is why this spring constant has to be like it is. This spring constant has to be newtons per meter, because that way when I multiply that by meters squared, then I cancel out one of those meters and I'm left with Newton meters. Newton meters is the same thing as joules. If you switch this and put meters per Newton, then you won't get joules out of this calculation. So this is why when you do graphs involving energy with springs, this is why you have to have that constant of newtons per meter. That way you end up with Newton meters, that's why you end up with joules. Okay, so what do you get out of this?
Like 3.
Well, it's got to be less than 0.938. What'd you get?
0.15.
Exactly?
Yeah.
Okay? So that 0.15, hold on. Now, everything still has to add up to 0.938.
It's still moving.
So how are you going to figure out how much? That's my us. I need my kinetic energy, so how am I going to get that kinetic energy?
Subtract.
Subtract it, because everything has to add up to this. So take 0.938 and subtract 0.15.
0.788.
Point what?
788.
So that's how much kinetic energy that I have. If I did this calculation and I got an answer bigger than 0.938, I have done something horribly wrong. Okay? Because I can't store more energy in the spring than the kinetic energy that I had to start with. Okay?
Supercharged spring.
All right. So, knowing that's my kinetic energy, Eli, I have my kinetic energy. I need to find the velocity. So, kinetic energy is 1/2 mv squared. So how can I get my velocity out of that?
Oh, you multiply by 2 and then divide by m and then square root all that.
Otherwise known as the Eli move. So, somebody take 2 times 0.788 joules and divide it by the mass. It was the mass, 0.3. Now, what does your answer have to be less than?
2.5.
2.5. If I get an answer bigger than 2.5, I've done something wrong. Okay? So, what'd you get?
2.29.
2 point what?
29.
2.29? Okay? So, we're still moving, right? We've slowed down some. Of course, we've only compressed the spring like this far. Okay? Good so far. So here's the last question on a problem like this. What is the maximum compression of the spring? So in other words, when this cart hits the wall and that spring is fully compressed, what's the maximum compression that the spring can have? Now, when it's fully compressed, what's the only type of energy that you have?
Potential spring.
Us. You got us. This is all about us, right?
Sorry, bro.
There's no UG, there's no kinetic energy. So if you go back up to your chart, and this is the beauty of this chart. Oh, that's 0.938 joules. If it's fully compressed, How much kinetic energy do you have?
Zero.
Zero. How much of do you have? Zero. How much us do you have? It's all about us. So,
The Earth is revolving around us.
kinda, in that case, yes. So us equals 1/2 kx squared. So, Michael, how am I gonna get x by itself?
You're gonna multiply, or I guess just say the Eli equation.
No, this is the Michael move.
Oh, this is the Michael equation.
Multiply by 2, divided by k.
So I got 2us divided by
K.
equals, and the square root of that. Beautiful.
There, you
So
got
it's
both
similar,
equations.
but it's us versus k, right?
K. Yeah.
So somebody take 2 times, what was it, 0.938? Divided by 3.00 times 10 to the third. What do you get?
0.025 meters.
Divide
0.0 what?
0.25.
Wait, what is that?
250,
0.225.
0.025?
Yeah.
Oh, there's another 0 in there I need.
That's ugly. Plus is on.
Now, hopefully that answer makes sense, because when it was 0.01 meters, we were still moving.
Yeah.
So that answer had to be bigger than 0.01. Okay? Go with this.
Yes.
So, now here's how you can make this more complicated. So then you can say, okay, if the cart was rolling, it hits the spring, it's all compressed, then it's going to bounce off the spring and then it's going to roll up the hill.
What? Oh.
Now, if it rolls up the hill, how could you figure out the height of the hill?
Mass times gravity times height.
Is going to equal what?
The
Well, what's the total amount of energy that's in the system?
0.938. Never mind, you don't
0.938.
even
Guess
need to
what?
do
You'd
that.
set MGH equal to 0.938, and then you would solve for height. Okay?
Oh,
So-
no.
What?
He's gonna have us do that.
That's not bad. Okay? All right.
Get it? I'm gonna get hit
Got it?
hard
Good,
just to
man.
get it. Use your just way later.
What?
Are you gonna be throwing like friction forces and stuff at us in the future?
No. Not for now.
Not for now.
What about
These are all IPOI situations. Yeah, stop
Test
that.
those.
That's sounding
The fourth right. I don't speak to.
Hold on.
I actually called these.
Okay. So, let me kind of get you started on some of these questions. So, when you get to question number 4, spring is 5.6 centimeters long when it's at equilibrium, okay? So, it's going to be a spring like this, 5.6. That's the length of the spring, okay? Then it says, I'm going to suspend a 0.2 kilogram mass, looks very similar to this, and the new length is 15.6. So we're going to go from 5.6 to 15.6. Remember, you are plotting elongation, you are not plotting length, okay? So you need to plot how far it's stretched, not the length of the spring, okay? You have to keep that in mind. Now, as Justin pointed out, on number 6, we have a box of purple crayons. When I typed it up, purple sounded like a good color, okay? So, 0.2 slides frictionless surface going at 4 meters per second, hits a spring. So number 6 is very similar to the problem that I just worked up on the board, okay? Now, when you get to number 8, okay? So, if you've never seen bungee jumping, so we're going to kind of model a bungee jump here with Al, okay? So let me kind of give you a visual about what's happening here. So you got a bungee cord, right? So here's Al, he's standing on top of the bridge. So Al is going to jump off the bridge, and what's going to be important is that Al is going to be in a state of free fall. So if you look at these numbers, an unstretched length of 12 meters. So what that means is that this person is going to fall for 12 meters before they begin to stretch this out, okay? Because that's kind of the throw. So you go boink, okay? So you're going to fall for 12 meters. Then, at the end, when you get down at the end, you're going to be 31 meters below like this. So you're going to fall for 12. You're going to end up 31 meters down below. So how far does the bungee cord stretch? 19, right? Okay? It's going to stretch 19 meters. So let me give you a hint on how to start this problem. Reverse engineering. Imagine that you're 31 meters below the bridge. Okay? If you're 31 meters below the bridge, how much work or how much UGG would you have to create to take you from 31 meters below the bridge and lift you up? Well, how would you calculate that number? Just MGH, right? So this one you kind of have to work backwards. You go, okay, I was going to start here at 31, right? 31 meters down below. Find that amount of energy using MGH. That's going to be the amount of energy that's in the system. Now, what you want to look at is that that energy there has to equal the energy that it takes to stretch the spring. Okay? That's the whole key to this. So you're going to set the UGG at the bottom equal to the amount of energy that it takes to stretch the spring.
So you're in free fall.
So, let me give you a hint. Set UGG equal to us. You're going to know how far it's going to get stretched. You're going to use the 31 meters for the H. Find the value of K. All right? Okay. There you go. Now, this is going to be due the Monday after Thanksgiving. Okay?
You're telling me you can
So tomorrow we're going to do Africa Day. I'm going to make ranch scrambled eggs tomorrow.
ranch.
Yes.
Let's go.
So if you guys want anything else, chips, dip, drinks, whatever, that's all on you. Okay? Now, can somebody bring you just like a dozen eggs tomorrow? Got it? Dozen eggs. Don't forget. Okay? Dozen eggs. Can you bring one too, just in case?
2 dozen.
Okay, just that way we'll have enough eggs. So you bring a dozen, you bring a dozen. Okay, and I'll provide everything else.
And I'll take the extra eggs home.
Okay. All right. We're good.